In the lesson on acids and bases, we started throwing around structures that had charges on certain atoms. We started seeing positive charges on some hydrogen. In fact, H+ is characteristic of an acid, and we started seeing negative charges at the end of an acid-base reaction. So in this lesson, we're going to systematically examine when you need formal charges and which formal charge you need to put on a particular atom. Okay, so starting with the big picture. In an earlier lesson, we derived the fact that carbon forms 4 bonds, nitrogen 3, oxygen 2, hydrogen and the halogens 1 bond, by looking at number of valence electrons and number of available orbitals. What I now have to tell you is that those rules imply that there is no charge on that atom. We can actually have a different number of bonds for each of these elements if there is a charge on that particular atom, and we'll see how to handle that in this lesson. Okay, so the details. Let's start with oxygen. This is something that should be fairly familiar to you. You've all seen an example of oxygen forming 3 bonds, namely H3O+. Okay, oxygen in this case has 1 lone pair. It's forming 6 bonds. It has 8 electrons around it. And H3O+, of course, is the product that you get when you take a strong acid and put it into water. You've also seen an example of oxygen forming 1 bond, OH minus the hydroxide ion. This is what happens if you take a strong base and put it into water. This oxygen has 3 lone pairs around it, is forming 1 bond, and has a negative charge. It's what you get if you take water and remove a proton from it. Okay, so we can get some rules that work for oxygen, and as it turns out, they also work for nitrogen. If these elements are forming an extra bond, such as H3O+, oxygen forming 3 bonds, they need to have a positive charge. And if these elements are forming 1 fewer bond than normal, like an OH minus, oxygen's forming 1 bond instead of 2, they need to have a negative charge. Okay, so let's drill down a little deeper and examine why this is the case. Well, oxygen normally comes with 6 valence electrons. That's what it means to be in group 6 of the periodic table. And in a molecule that contains a neutral oxygen, there are 2 lone pairs on that oxygen. 4 of the valence electrons are in those 2 lone pairs, and 2 of the electrons are unpaired. Therefore, oxygen can form 2 bonds. It has 2 available orbitals. In order for oxygen to be able to form 3 bonds, there have to be 3 available orbitals. And when I say available orbitals, I mean not completely filled and not only 2. In order to have 3 available orbitals, that's 3 valence electrons, there can only be 1 lone pair, so there can only be 5 valence electrons on oxygen if it's forming 3 bonds. Now, to use this next analysis I'm going to go into, we need to add in the 1s electrons, the core electrons. So oxygen with a positive charge has 5 valence electrons, the 2 core electrons for 7 total electrons. Oxygen has 8 protons. That's what it means to be oxygen, to have atomic number 8, but only 7 electrons around it. Therefore, it must have a positive charge. If oxygen is forming only 1 bond, that means 3 of its orbitals must be filled. If it had 2 available orbitals, it would form 2 bonds. Oxygen would like to be neutral and would be happiest if it could form 2 bonds. But if there are more electrons around it, such that 3 of its orbitals are completely filled, that's 6 electrons. There is 1 half-filled orbital, that's 1 electron, and therefore it has a total of 7 valence electrons. Again, adding in the core electrons, that oxygen would have 9 total electrons. 8 protons and 9 electrons means that it must have a negative charge. What about nitrogen? Same analysis. Okay, NH4+ is an example that you've seen repeatedly of a positively charged nitrogen. So nitrogen here is forming 4 bonds, therefore it must have 4 half-filled orbitals. The maximum number of valence electrons then has to be 4. If it had the 5 valence electrons that it would like to have, one of them would be taking up both would have to be paired up. There would have to be a lone pair, so there would only be 3 available orbitals. So with 4 valence electrons around nitrogen, there are 6 total electrons adding in the core electrons. So 7 protons, definition of nitrogen, 6 electrons, overall positive charge. What about NH2 minus? If nitrogen's only forming 2 bonds, that must be because 2 of the orbitals are completely filled. So if you have 2 orbitals that are completely filled, that's 4 valence electrons, 2 that are half filled, that's 2 more valence electrons. So that would give 6 valence electrons. Adding in the 1s gives you 8 total electrons. 7 protons and 8 electrons, you have a negative charge. Okay, what about carbon and hydrogen? Carbon and hydrogen cannot form an extra bond, or else you would violate the octet rule. Shell 1 for hydrogen is limited to 2 electrons. A bond has 2 electrons. If you tried to form 2 bonds to hydrogen, you'd be putting 4 electrons around this hydrogen, and that violates the octet rule. And then similarly for carbon, if you have 5 bonds to carbon, that would be putting 10 electrons around that carbon and violating the octet rule. However, both of these elements can form 1 fewer bond without violating any fundamental rules of nature. Okay, so these structures in which hydrogen is forming 0 bonds or carbon is forming 3 bonds can have either a positive or a negative charge, depending on whether that non-bonding valence orbital, the valence orbital that is no longer participating in a bond, is filled. In other words, it has a lone pair in it, or it is empty. All right, let's look at hydrogen first. Hydrogen with no electrons is simply the proton, H+, and the 1s orbital is empty. It is forming no bonds. You're familiar with H+. You may be a little less familiar with H-, which is when the 1s orbital has 2 electrons in it. 1 proton, 2 electrons needs to have a negative charge, and that is called the hydride ion, and in this case the 1s orbital is filled. Right. What about carbon? The 2 options for carbon, I'm first going to handle carbon with a negative charge. You're probably not familiar with carbon with either a positive or a negative charge. So carbon with a negative charge, it's forming 3 bonds, has a lone pair on it, and it is called the carbanion. Anion standing for something that's negatively charged. We can analyze this the exact same way that we analyzed NH2-. We have 8 valence electrons around carbon. Okay, 6 of them are in the bonds and 2 of them are in the lone pair. Therefore, this structure must have trigonal pyramidal geometry. There's 4 electron pairs, but only 3 groups bound to it, and sp3 hybridization. The carbon contributes 5 valence electrons, 2 in the lone pair and 1 in each of the 3 bonds. Add in the 2 1s electrons, and there are 7 total electrons on carbon. 6 protons, what it means to be a carbon, and 7 electrons means you need to put a negative charge on it. The other option is the carbocation, in which you have an empty orbital on carbon rather than a filled orbital on carbon. In this case, there are only 6 valence electrons around carbon, and only 3 of them are coming from the carbon. The others, of course, are coming from the R groups. When you have only 3 things bound to carbon and only 3 electron pairs around carbon, you're going to have trigonal planar geometry, so the hybridization is going to be sp2, and there will be an empty p orbital. This is your first introduction to the carbocation, but as you will see, the carbocation is a very important intermediate in many of the reaction mechanisms that you will be learning about in the first semester of organic chemistry. So get to know the carbocation very well. In terms of the electron counting for it, Carbon is contributing 3 valence electrons, add in the core electrons, and you have 5 total electrons on carbon. 6 protons and 5 electrons means you have to have a positive charge. Okay, I've gone through this analysis because students frequently make the mistake of what charge am I supposed to put on it, and in some places guess whether they're supposed to put a plus or a minus. Now you have a very systematic way of knowing which charge you're supposed to put on. And then furthermore, carbon is the most electronegative element that can be electron deficient, meaning having an incomplete octet. Okay, you may wonder why, well, couldn't I do the same thing with nitrogen or oxygen? Can't I have a nitrogen forming 2 bonds and having an empty orbital? Can't I have an oxygen forming 1 bond and having an empty orbital? Those are simply not stable structures. They're not things that we will routinely observe. They could be under very, very odd conditions at low temperatures in the gas phase. But in general, those structures can't be observed because nitrogen and oxygen are just too electronegative. They want electrons too badly that they're not going to become electron deficient. Now, there's an alternative way of thinking about what I've just given you, and that's if you like algorithms. If you want to just memorize a formula and know exactly how to get the right answer from the formula, there is a formula that you can use to get the formal charge on an atom based on its number of bonds and lone pairs. And the formula is as follows. F equals Z minus B minus U, where F is the formal charge on an atom, Z is the group number of that atom on the periodic table, B is the number of bonds that that atom is forming, and U is the number of electrons in lone pairs. Not the number of lone pairs, the number of electrons in the lone pairs, also known as the unshared electrons, which is why it's U in the formula. Okay, so let's look at a couple of examples of just how the formula gets put into practice. If we look at NH4, which we already know what answer we're expecting for, Z is 5, you're in group 5 of the periodic table. It is forming 4 bonds, has no lone pairs on it. 5 minus 4 is equal to positive 1, so therefore you expect to have a positive charge. As a second example, we're going to look at OH. Oxygen's in group 6 of the periodic table. It is forming 1 bond, and there are 6 electrons in lone pairs. So 6 minus 1 minus 6 is equal to negative 1. Therefore, we would expect there to be a minus charge on OH, and there is. Okay, now that we have gone over the rules on how to assign formal charges, where we will go next is talk about how you get these charges on particular atoms through the cleavage of bonds from neutral precursors. So to go over that, the next lesson we'll talk about the 2 types of bond cleavage, homolytic and heterolytic bond cleavage.